Welcome to Maths with EJD. In this video, I'm talking about partial differentiation of vectors. In the video before this, for vectors, I talked about differentiation of vectors, but it is really important to consider the partial differentiation of vectors because it throws up some very useful ideas in vector, should I say vector calculus now? So, and talking about partial differentiation of vectors, there are three very important things we have to consider, and those are gradients, divergence, and curl. And let's see what all of this mean. Let's start with gradient of a scalar field. Gradient of a scalar field. Gradient of a scalar field. So the gradient of a scalar field, f of x, y, z, is a vector field, is a vector field that points, it's a vector field that points in the direction of the greatest rate, of increase of the scalar field. Okay, so the gradient of a scalar field, f of x, y, and z, is a vector field that points in the direction of the greatest rate of increase of the scalar field. So you have a scalar field, right? And it is increasing in all directions or at all points, right? So the point at which it increases the most, that is where the gradient is pointing, okay? So having said that, the magnitude of the gradient, of a scalar field represents the rate of increase in that direction. Okay. So, of course, this is like some story in the background, but let's have some kind of mathematical definition. So let's do some mathematical definition. Okay. So for a scalar field, f of x, y, and z, the gradient is defined, as this symbol. I think it's nabla. I think this is called nabla f, which is more like d dx, comma d dy. That's partial. We're talking about partial differentiation of vectors. So partial x, partial y, partial z of f, which is actually the same thing as saying nabla f is equal to partial f, partial x, partial f, partial y, and partial f, partial z. So that's partial derivative with respect to each of the components. Okay, to drive the point home, see what we get. So we have this. Of course, now you can see saying all this is actually exactly saying this. Of course, another representation of this will simply be, we said it's actually a vector. The gradient of a scalar field is a vector field. So, I mean, this is a vector representation, which is actually the same thing as partial f, partial x, in the direction of I, partial f, partial y, in the direction of j, and partial f, partial z, in the direction of k. So it's still a vector, right? So let's have an example. So we have this example. That to consider the scalar field, f of x of y of z is equal to x squared. Okay, I was wondering if that space would be enough. So it's better to go down so we don't miss the space. So you have f of x, comma y, comma z equals x squared plus y squared plus z squared. Okay? So consider this scalar field. Okay? So, and the first thing we want to do is to compute the partial derivatives. So we compute, first step, compute the partial derivatives. Partial derivatives. Okay, want to compute the partial derivatives. So partial f partial x is equal to so partial x of everything, x squared plus y squared plus z squared. So you see, the only one that works, partial f partial x would be 2x, or partial y squared partial x would be 0. Partial z squared partial x is also 0. So partial f partial x is simply 2x. Then we have partial f partial y, and that is partial y into x squared plus y squared plus z squared. So here, the focus is on y squared now. So because partial x squared partial y is 0, partial z squared partial y is also 0. So partial y squared partial y will be 2y. That goes. Of course, the same applies to z. So partial f partial z is equal to partial z of x squared plus y squared plus z squared. And then we know this only applies to z squared now. The answer is simply 2z. And once you have that, right, we can say that thus the gradient is, okay, or we can say the gradient of f of x, y, z, which is x squared plus y squared plus z squared, is grad f. Of course, this is another way to write this. You can say it's grad f, which is the same thing as 2x. That's, of course, those partial things you have. 2x, 2y, 2z, which is gradient which is also vector representation. And you can also write it as 2xi plus 2yj plus 2zk, like that. So that is the idea of grad. And then what about the interpretation? What does this translate to? What does it mean in reality? So let's talk about the interpretation of this. Interpretation. So the gradient, grad f or nabla f, if you like, at any point, x, comma y, comma z, points radially outwards. It points radially outwards and has a magnitude that increases. That's a magnitude that increases with distance from the origin. Okay. So as the distance increases from the origin, the magnitude also increases. So this indicates that f increases. This indicates that f increases most rapidly in the direction of the gradient, in the direction of the gradient. Okay. And of course, this aligns with the opening statement, right? Because we said it is that point. It is the point where it's actually a vector field that points in the direction of the greatest rate of increase. So this aligns with what this interpretation is saying. It indicates that f increases most rapidly in the direction, most rapidly in the direction of the gradient. Okay, so that's about gradient of a scalar field. So gradients are applied to scalar fields, as we can see already. Now let's talk about something else. Let's talk about another important idea, which is divergence. Divergence of vector fields. Divergence of vector fields. So when we talk about divergence of vector fields, right, the divergence of a vector field F, of a vector field F. So here now F is a collection of vectors F1, F2, F3. Of course, you know that's like F1I plus F2J plus F3K. Is a scalar field, is a scalar. So you see, the gradient of a scalar field is actually a vector field, but then the divergence of a vector field is a scalar field, as you can see. So it is a scalar field that measures, that measures. So you see that the result of gradient is vector, but the divergence of vector is a scalar. So that's why you expect the answer whenever you do gradient, you expect a vector. Whenever you do divergence, you expect a scalar. All right. So the divergence of a vector field, this is a scalar field that measures the net rate of flux expansion, net rate of flux expansion or contraction at a point. Contraction at a point. Okay. It is given by nabla dot f. This is a vector now. And that is partial f1 partial x plus partial f2 partial y plus partial f3 partial z. So that is the divergence of a vector field. And this results to a scalar by definition. Okay? So if we have, for example, example, if we have if you consider this, consider the vector field, the vector field, the vector field F, which is equal to x squared plus y squared plus z squared. Oh, sorry, not plus at all. They are components. So it's x squared comma y squared plus z squared. I think, of course, it's different from the other time when we had x squared plus y squared plus z squared. So this is x squared, y squared, z squared. So consider this vector field that. So we compute the divergence, compute the divergence. So if you compute the divergence, that is nabla dot f, which is d dx of x squared, component by component, plus d dy of y squared plus d dz of z squared. Okay? And that's simply the same thing as 2x plus 2y plus 2z. And that's it. So that's all you get for this. So you can see that it's a vector now. So it looks like you're doing it's a dot product of the nabla and the force field, which gives you a scalar. And then the interpretation is always of essence. Let's talk about the interpretation. Interpretation. So the divergence tells us that the vector field, F is expanding away from the origin, from the origin as the components increase, as the components increase linearly with x, y, and z. Okay, that's the interpretation of divergence. So since we talked about divergence of vector fields, now let's go and talk about the curl of vector fields. So curl of vector fields. So talking about curl of vector fields, right? The curl of a vector field F, which is F1, F2, F3, is another, it is another field. Okay, better still, it is another vector field. So now the result you expect from here is a vector. So it's another vector field that measures, so this measures rotation and circulation, measures the rotation or circulation at a point. So divergence is some kind of stretching, you know. Gradient is some kind of radiation from a point. Like from a point you have things shooting out. But divergence is like a kind of stretching out. But here we are talking about rotation at a particular point. So the curl of a vector field F with F1, F2, F3 is another vector field that measures the rotation or circulation at a point. It is defined as, so now a cross vector. So you have nabla cross the force field, and that is, you have component by component. Well, I think the basic thing is this. When you have this kind of thing, right? It's basically this. You have I, J, K. You have I, J, K. Then you have, for nabla now, you have partial X, partial Y, partial Z, and then you have F. That's F1, F2, and F3. So that you can now work this out. So you already know that this is, of course, this is plus, minus, plus normally. So you have I outside here into, so when you have I outside, cross the column, cross the row. So you have partial, so partial F3 minus partial Y, partial F3 minus partial Z, partial F2. So that's partial, so that's partial Y, partial F3. No, this is rather partial Y of F3. So that's partial F3, partial Y, minus partial F2, partial Z. Okay, like this. Then the next thing is what? The next thing is, if you remove this now, if you remove this, then now cross out. So now you have minus J. So you have minus J like this. Cross out the column, cross out the row. Of course, this can go now. So here we have partial F3, partial X, minus partial F1, partial Z. So partial F3, partial Z, minus partial F1, partial X. And then lastly, of course, if you get rid of all this again, okay, so you have plus K into, cross the column, cross the row. So that's partial F2, partial X, partial F2, partial X, minus partial F1, partial Y, partial F1, partial Y. Okay? So that is this cross F. That's cross F. So that simply means that of course you can have it this way, or you can put it in that representation we always have. That is partial F3 partial Y minus partial F2 partial Z. That's partial F2 partial Z. Okay, comma. Of course, this is minus, right? So if you move this minus inside, so that'll be minus partial F3 partial Z. Then minus becomes plus. So we can have partial F1 partial X minus partial F3 partial Z. Okay, comma. Then the last one, we have partial F2 partial X minus partial F1 partial Y. So, and that is the cross product. Okay. That's the curl of a vector field. So let's take an example. So imagine that we have this example. Consider the vector field. Consider the vector field F, okay, which is the vector field F, which is actually 0, 0, X, 0 in the directions I and J each, and then X in the direction Z. So if you compute the curl, which talks about rotation. So you simply have del cross F. I think this is called nabla or del, del or something like that. But I know this, it's a Greek symbol called nabla or something. So del cross F is equal to, okay, I mean, the easy way to go is you have, this is a cross product. You already know how to do cross product from our previous video. So if you don't know that, you can refer to vector operations. That must have been like the second video. So you have IJK, and then for del now you have d dx, d dy, and d dz, and then this is 0, 0, x. So we just have this to be equal to I is outside, of course, plus, minus, plus. I is outside, and cross this and cross this. So it means you have d dy of x, okay, minus d dz of 0. I mean, by that, I mean this minus this. So we have that. Then next we have minus j. So minus j now. We have minus j into cross the column, cross the row. So we have d dx of x, that's this, minus d dz of 0, that's d dz of 0. That goes. And then finally, we have plus k. Of course, this can go. So, and of course, this. So we have cross the column, cross the row. So we have k into d dx of 0, d dx of 0, minus d dy of 0, d dy of 0. Okay, I mean, because of the zeros, this is somewhat simple, so that we go. So this is I into d dy of x is 0, d dz of 0 is 0 also, minus j into d dx of x is actually 1. That's differentiate x with respect to x. Then d dz of 0 is also 0, plus k, into 0 minus 0 also. So at the end of the day, just have I into 0 minus j into 1 plus k into 0. So that means you have 0 minus j plus 0 also. So at the end of the day, you have curl cross F to be minus j. Okay, so that's all we have for that. So that means this is actually the same thing as so that's like in the direction of j, right? Yeah, dx dy minus dx. Yeah, this is 0, 0, x, right? Okay, so this is just in the direction of J. So that means we have 0, -1, 0. 0 -1, 0. That's what that is. So that's what we have. 0, -1, 0. Yeah, that's what we have. So talking about the interpretation, interpretation. So what is the meaning of curl? So the curl vector, the curl vector, the curl vector 0, -1, 0 indicates that the field F, has a rotational effect, around the y-axis, That's what this simply means, because no effect at other points. All right, so that's the second part. Can we talk about the last part of this video, where we talk about applications in electromagnetism? That's application of partial differentiation of vectors in electromagnetism, and fluid dynamics and here we have been talking about fluid, we're talking about rotation and all that. So electromagnetism and fluid dynamics. Okay. So that first of all, talking about electromagnetism. So for electromagnetism, so the electric field, okay. So for electromagnetism, right? Let's talk about gradients. We are talking about partial differentiation of vectors. So gradient is the first of them. So the electric field, E, which is a vector, right, is related to the electric potential, V, by E equals minus del V. Okay, this is like this is grad V, because so this is actually grad V. So this is like gradient. So let me do that better. So this is grad V. Okay, that is the electric field. The electric field E is related to the electric potential V by E equals minus del V, or minus grad V, if you like. Okay, then we talk about divergence. How does divergence play out in electromagnetism? Divergence. That's the dot product of this guy, del, if you like, or nabla, and a force field. So talking about divergence now, say Gauss's law for electricity, Gauss law for electricity states that del, this, you can say this is del dot E. So that's the electric field, I believe. So del dot the electric field is actually rho divided by epsilon naught. Rho divided by epsilon naught. That is the Gauss law for electricity. So where rho is the charge density. Rho is the charge density. And of course, talking about curl, what role does curl play in electromagnetism? Faraday's law. of induction, magnetic induction and all that. Faraday's law of induction states states that it states that the del I have to write that properly, that the del, okay, cross the electric potential. Oh, is it the electric field now? It's the electric field. So del cross the electric field is actually minus partial B, partial T, where B is the magnetic field, is the magnetic field. Of course, being a magnetic field, it's actually a vector. So of course the whole idea of electromagnetism is about how magnetism can cause electricity and how electricity can cause magnetism. So that's all that. So we see that grad, dive, and curl all have applications in electromagnetism. So talking about the relationship between electric field and electric potential for gradient, the Gauss law for divergence, and the Faraday's law of induction for curl. So the Gauss law for electricity for divergence, that is. So let's move to fluid dynamics. So let's look at the application in fluid dynamics. So application of partial differentiation of vectors in fluid dynamics. Fluid dynamics. Okay. So first, in fluid dynamics, these operations describe the behavior of fluid flow, generally speaking. Okay. One thing I forgot to talk about up here is this, that in electromagnetism, the gradient, divergence, and curl operations are used. They are used in Maxwell equations. So all these things we broke down are actually part of the Maxwell's equations. So the whole electric field and electric potential, Gauss law of for electricity, and Faraday's law of induction, they are all part of the Maxwell equations. So talking about fluid dynamics now, in fluid dynamics, these operations describe the behavior. They describe the behavior of fluid flow. They describe the behavior of fluid flow. First of all, talking about divergence. So divergence. So the divergence, divergence talks about some kind of stretching out or radiation from a single point, or think of fluid flowing from one point or something. Let's see. So the divergence of the velocity field, divergence of the velocity field V, it's a velocity in fluid dynamics, represents the rate of change of fluid density at a point. The rate of change of fluid density at a point. So we see that for incompressible flows, I mean, this is where we talk about all this Newtonian flow and things like that. For incompressible flows, we see that the velocity field is actually equal to 0. So that means that there's no stretching out, okay? There's no stretching out. Or there's no there's no change. So the fluid is incompressible, right? So that's that. Then we talk about the curl again. Here there's no gradient. So let's talk about so we have just divergence and curl. So for curl now, So we can say that the curl of the velocity, the curl of the velocity field V, of the velocity field V represents the vorticity for TCT of the fluid, indicating rotation or circulation within the fluid. Rotation or circulation within the fluid. Okay. So let's take an example in fluid dynamics. Example in fluid dynamics. In fluid dynamics. Okay. So for a velocity field, V, which is equal to minus y x comma 0, which represents a simple 2D flow, a simple 2D rotational flow. It's 2D because the third part is 0. A simple 2D rotational flow. Okay. Let's compute the curl. Again, we know that is a vector product. So that is del cross V. Del cross V, which is again I, J, K, then partial X, partial Y, then partial Z, and then you have minus y x 0, minus y x and 0. And again, we know how that goes. So this is equal to I into cross this and cross this. Of course, this is plus minus plus like we know. So that's plus I into d dy of 0. That's this now. Minus d dz of x. That's this. We cover that up and then we continue. Okay. Then we have minus j, so cross the column, cross the row. So this minus j now. So we have d dx of 0. This now minus d dz of minus y. That's d dz of minus y. Okay. And that goes. And then we can move to k. So that is plus k, right? So we have plus k. That is this k, cross the column, cross the row. So we have d dx of x, that's d dx of x minus d dy of minus y, d dy of minus y. So we have all that. So we can tidy this up now to see what we get. So this is I into d dy of 0 is 0, dz of x is 0 because differentiating x with respect to z is 0, then minus j into d dx of 0 is 0, dz of minus y is 0 also, then plus k into d dx of x is 1, so minus d dy of minus y. That's minus 1 again, okay? That's minus 1. So we have I into 0, mean I into 0 minus j into 0 also plus k into 1 plus 1. So we have 0i minus 0j, okay, plus 2k. So that means that our del cross v is equal to 0, 0, 2. 0, 0, 2. That means rotation is only happening in the around the z axis, as we already know, because this is about rotation or rotation and circulation. Yeah, rotation and circulation. So this shows this shows a constant, vorticity, of 2, a constant vorticity of 2 in the Z direction, that Z axis, in the Z direction, indicating the fluid is rotating. The fluid is rotating around the Z axis. Okay, so these concepts are fundamental in understanding various physical phenomena and solving practical problems in fields ranging from engineering to physics. So thank you so much for listening to this video on partial differentiation of vectors, and you have seen the applications in both electromagnetism and fluid dynamics. Thanks for always stopping by. If you have not signed up to this channel, if you have not subscribed, please be sure to do that. And don't forget to hit the notification bell so you can always get alerted when a new video is released. And of course, don't forget to comment, like, and share. For instance, this series on vector, it actually came as a special request from a friend who would like some clarity on this. So feel free, if you need to learn about something, comment about it somewhere. If you're saying this on Facebook or wherever, just let me know. I might just be able to have time to consider your request. Till then, see you. Bye.